Let's see. So for example, for the question 7, you have this. You get the, you are going to derive this. The question 7 on the midterm exam. What's going on? Da, da, da. For the question 7 on the practice exams, and then it's asking you to derive the 3 points quadratus rule, right? And for this one, actually you have several methods to do it. So let me remind you of the 3 points quadratus. And for the method 1, before this one, and then actually we need to use these things for the following several methods. So first, my question is, what is the degree of precision of the of this 3 point quadratus, Gaussian quadratus? What is the degree of precision? So the degree of precision is just 2 times the number of the points you use, and then -1, right? 2n minus 1. And then the n here is just 3 and then -1, and then which means that we have the degree of precision of 5. And which means that the Gaussian quadrature rule, the 3 point Gaussian quadrature rule is except for the function f(x), and then x equals to x to the order n, and then n equals to 0, 1, 2, 3, 4, and 5. So if we plug in the f(x) into that formula, and then it should be exact. And then what is the formula? The formula, it should be the -1 f(x) dx. And then this is the integral we want to approximate with the Gaussian quadrature rule. And then that Gaussian quadrature rule is just a C1 fx1. And then we have 3 nodal points. So we have 3 nodal points here, and then 3 corresponding coefficients here. We want to know C1, x1, C2, x2, C3, x3. And this is the question 7. And now for the method 1, what you can do is to, so method 1 is to plug in the fx equals to the xn. And then when for the n equals 0, 1, 2, 3, 4, 5. For examples, and then the first one is the x to the order 0, and then you would get -1, 1, and then the integrations of fx is just equals to 1 here. X to the 0, and then equals to 1, and then this is the first things you have in the method 1, and then on the left hand side you get the integration. The integration equals to 2, and then you have on the left hand side, right hand side, because this is the degree of precision definition, and then it means that the Gaussian quadrature rule is exact, which means that for this function fx equals 1, this is no longer this is not just the approximately equal to, and then we actually have the equal sign here because it's exact. So now we have on the right hand side, and then it's just a C1, and then times the function evaluated at the nodal point 1, x1. So it's just a 1 because the function is a constant function here. And then we got C2 times 1, and then C3 times 1 here. And this is the first equation you get for the nodal points and the C1, C2, C3. And you are going to keep plug in fx equals to x, fx equals to x squared, fx equals to x cubic, and fx equals to x4, and then fx equals to x5, and then you get 5 equation, and let's solve for the C1, C2, C3, x1, x2, and then x3. Does that make sense? This is the method 1, in which I don't suggest you to do such a things, because you will have to solve six equation, six equation, and you have somewhere here, if you take a look at the 5 equation, and then the 6th equation, you would get, you need to do -1, 1, and the x to the 5 dx, and then on the right hand side, the things will become very complicated. This is not just a linear system of the linear equation. You have system of nonlinear equation, because you have C1 x1 to the order 5, C2 times x1, x2 to the order 5, C3 times x3 to the order 5. So you have some nonlinear things here. You have the order more than 1, and then so this system of equation is hard to solve. So this is the method 1. If you don't know, if you forget and other things, and then you can still use this method to try to solve out the C1, C2, C3, x1, x2, x3 for your exam. And then for the method 2, this is a better one. Let me give you one. Let us record that what we have here. So this is a general way to get the nodal points, and this is what the theorem stating. The nodal points of the nodal points for the Gaussian quadratures are the roots of the nth Legendre polynomial. So now we want 3 nodal points, which means that we want this, the P3 here, and then we want to solve the P3x equals to 0. And then we get 3 nodal points. And let me just copy down the P3x here for a moment. P3x equals to the x cubic minus 3/5, and then x. So I would give you some things here. The first few Legendre polynomials in the cheat sheet. And let's go back to what we have on the method 2. In the method 2, so P3x, and then we want to know the nodal points, right? And then we solve P3x equals to 0, which means that we have x cubic 3/5x, and then equals to x squared minus 3/5, and then equals 0. And we got x1, and that equals to 0, and x2 equals to negative square root of 3/5, and the x3 equals to square root of 3/5. Does it make sense? So this is good because compared to the method 1, we actually have 6 unknowns, right? But now we already get the x1, we already get the x2, right? And now we already get the x3. And that's a good one. And you can keep doing these things as the method 1, but you just need to plug in the first 3 polynomials, basics polynomial. So we are going to plug in the fx equals to 1 here, x to the order 0, and then equals 1. And you will see now, instead of having a system of nonlinear equation, and then after you get the nodal points and then do the plotting, and then actually you will get a system of linear equation. For the method 1, you will get some nonlinear things, but for the method 2, you will have a system of linear one, and then it's easier to solve. And then you can use your calculator to solve the linear equation. And remember to bring your calculators on that day, and otherwise, I cannot give you a calculator to calculate the things you want. So for here, you are doing the same plot in here, but here you have C1, 1, and then plus the 1 times C2, and then 1 times the C3, right? But the good things is that once you get to the fx equals to x to the other 1, and then it's just x, right? Here you're going to do the integration here, and then it equals to 0. And the good things is that if you plug in fx1 and the fx2 and the fx3 there, and then we actually get some value here, and then that is just the fx1, and then which means that the x evaluate at the x1, and then it's just the x1 is equals to 0. So the first things we get is 0, and then times c1, and then for the second one we get negative square root of 3 and then 5. This is because we have that this one is the fx2 and times the c2, and then square root of 3 over 5, and then times c3, and then this is the fx3. And you will see this is linear equations about the c1, c2, c3, and fx. The next things we are going to plug in the cx2, x squared, which gives us the f negative 1 x squared dx, and is if we do the integration, it's just the negative 1, and then it's just the it equals to 2 over 3, right? And on the right hand side, there's another good news. Once again, we get a linear equations about C1, C2, C3. They are not linear equation, which means that the order of the C1, C2 is just with order 1, and the order unknowns are with order 1. And if you take a look at here, what we have is just the we plug in fx1, and then that is just a 0, and then square, because this is our fx functions right now, this one. And I just get the 0 square, and then I got this one and c1 plus negative square root of 3, 5 over 5, and then square, and then times c2, and then square root of 3 over 5 square, and then c3. And I stop the plotting here because I have 3 unknowns, and then that unknowns are C1, C2, C3. And then I have 3 linear equation, and then I can solve for C1, C2, C3. And this is how I get all the unknown values in the Gaussian quadrature through in the method 2. So I separate into 2 parts. So the first part, I get the nodal points by solving the Legendre polynomials equals to 0. And then the second part, I just do the first few plot in here. And then I solve the linear equation for the C1, C2, C3. And this is the things. And here, there's method 3. It depends on your preference. And for these 3 methods, personally, I love the method 2. And then the method 3 is just using the whole idea from the from this theorem 2. So the x1, x2, the nodal points are the roots of the Legendre polynomials, and the CI is just the integration. But I don't like how to use the integration here because I hate to do the integration. So I'm just copy down the whole formula here. And j equals to 1, j does not equal to I x minus xj, and then xi. I don't like to memorize the formula as well. I hate this. So, but in case that you love to memorizing things before the exam, and then I'm going to show you the ways to solve the equation, So for the coefficients here, so first of all, the first part is pretty the same as the method one, method two. You solve the Legendre polynomial and then to get the node points. And then once you get the node points, and then you can do the integration. And then, for example, we want to get a C1, and then C1 is just -1, 1. And then the integration should be, so here, the I equals to 1. So we get x1 and then minus x2 and then x minus x2 and times the x minus x3 and then x1 minus x3 and then dx. And which means that you need to do the integration -1, 1 x minus. This is just the addition here because there's a negative sign in the x2. And I got 0 and then plus this one. And then I got x minus square root of 3 over 5. And then 0 minus square root of 3 over 5 dx. This is how I calculate the C1 by using this formula, and then you can keep doing the things C2 and the C3. Actually, you need to use your calculator or you need to calculate it by hand, and then you get a number here, the C1. And then the C2, you can do the similar things. C3, you can do the similar things. So you can see why I love the second method, because it's just solving the linear equation. But this one, you need to do the integration here. And this is the question 2. And question 7. It's asking you to derive the formula. Let's see, for the question A, the question A would just ask you to apply that Gaussian quadrature rule. And on the actual exams, I would tell you, please just use the table values we have here. So let's see, what do we have in the question A? We are going to use the Gaussian quadrature rule to approximate this this integral here with 2 node points, right? And so what you are going to do is first, what's the degree of precision here? So could you answer me these questions, because I have already told you before. So how to answer this one? What is the degree of precision? You can use your thing, your hand to indicate how many degree of precision do you think here? 3, right? Yes, this is 2n minus 1. So we already get, like, if this is a 10 points question, and then you already get 2 points. And let's see how to do this. So I will give you a table here, and then at the end of the question, I will say, please use the table value. The table value given in the cheat sheet. And then so what you're going to do is to take a look at this table. And then this table, you have number of points, and then that is the true number of points we have, right? And then so we are going to use this block, and then we get the points value. And then the points value should be the x1 is the negative square root of 103, and then the x2 is just the square root of 103. And what do we have for the weights? Weight is C1 equals to 1, and then C2 is also equals to 1. Here, C1 is also equals to 1, C2 equals to 1. And the things you need to memorize is this. It's the change of variable. The formula of the change of variable, and then this is the things you need to know for the question A. I'm going to copy them here before I switch the screen to back to the iPad. Okay, so I just copy that. This is some things you get from the cheat sheet, and then on the table there, from the table there. And then this is some things you need to memorize, the change of variable. And the next things you need to do is to do the change of variable and -3. And then this is the original function. And then now what you get, let's see, change the variable to -1, 1. And I got, what is this? E and then X. X here is just the 1/2. And then what is B minus 1? B minus A is just the 3 minus. So for here we have the B, this one is our B, and this one is our A. And so B minus A is just 6, right? This one is just 6. So we got 60 here, and then plus the A plus B is just 0. So we just get 60 here. And then what is dx? Dx is equals to the derivative of x and then times dt. So the derivative here is just 1/2 and then b minus a, and then the 1/2 of b minus a is just 3. So we have 3 dt here. And now we are going to apply our, so at the end of the day, you get such a function, -1, 1, and then exponential 3t, and then times 3 dt. And now we are going to apply the Gaussian quadrature rule to this this function, and we get, so it equals to, so we are going to plug in here. So we have the 3 and then e and then 3 and then times the negative square root of 1 over 3. And then what is the coefficient? Coefficient is just 1. And then plus the 1, this is the coefficient C2. And then this is 3. And then do the plugging here, 3 times the square root of 1 over 3. And what's this thing? This is just the C1. And this is the, so this is the new function. Actually, this one is the new functions ft, and we are doing the integrations of the capital Ft, right? And then on the standard interval, -1 and 1. So what we are going to do is just the C1 times the F, and then evaluate at the nodal points T1. I'm just changing the value here. It's still more the X variable, right? But the value is the same. This is the nodal values on the standard interval, -1 and 1. So this is just a T1, C1, and then T1. And then for this one, it's just the C2. And then this one is just the function capital F function, and then you evaluate at T2. And next, you need to do some plotting here. Use a calculator to get the numeric number here. You can run it to like 5 decimal points or 2 decimal points. It's up to you. How many decimal places you need to keep, and then you can decide it. And then you get a numeric number here. Does that make sense? So this is the question 7 and 8. Any questions? I just saw your calendar. I want to sing the song, Baby Shark. Mommy Shark. Okay, let's see. Baby Shark doesn't have any questions, so let's move to the linear equation. Okay. I'm happy that no one having any question, but if you have any question in the exam, and then I cannot answer you, and I cannot have you out there, just jump to the sea if you have some questions in the exam, during the exam. Okay, good. So we are going to get to the next chapter, starting from this point. And we are going to use 20 minutes to get the introduction to the new chapter. So we are going to solve linear system of equation. So first of all, I need to ask some questions. So how many know this one? Gaussian elimination. I know most of you have already learned this from the linear algebra class. If you know that, please raise your hand. How to do the Gaussian eliminations? Gaussian eliminations. Who knows Gaussian eliminations? Okay. Not all of you know this one. So I need to take the time to explain the idea. So for those who you know this topic, and congratulations, you already get like 10 points for the final exam. So let's get to the idea. So let us just start from the very beginning, and then what is a linear system equation? So we have n unknowns here. And then they are x1, x2, and then to the xn. And we have a large linear system of equation. Equations, and they look like this. And then we have the A11, they are the coefficients, that is some number, and that we already know. And the A12 is also some number, we already know they are the coefficients. And then xn, and then we have the B1. B1 is the right hand side term, and then it's also a number. And then we have n similar equations, but we have different coefficients for them. And we have n equation, looks like this. And I'm going to mark out what we know and then what we don't know. And then Bn. So what we know is the A11, A21, An1, all these coefficients here. And then we also know the right-hand side. And the only things we want to know, we want to solve. And then that is the unknowns here. And then that's x1, x2, we don't know, x2, we don't know, and the xn, we don't know. And we want to solve this linear system equation. Of course, you can use some linear algebra knowledge to solve it, but if you have 100 unknowns and then 100 linear equations, and then I think you are going to do some ChatGPT, or you are going to use the online server, right? But what is the online server? What is inside that black box? And then they are actually using some numerical methods here. And so before we move to the introductions of some numerical methods to solve a large system of the linear equation, we are going to write it into the matrix format. And the matrix format, it looks like this. And then it's just the matrix A, and then times the vector X. This is the vector. And then this is also vector B vector. And what's the A matrix? The A matrix is just all the purple things on the left-hand side. And then that is C, A11, A21, A3, let me skip writing these things in between. And An1, A2, A12, this is the second column, A12, sorry, A12, A12, A22, and the An2. And all the things in between A1N, A1, A2N, and all the things in between, and then in the end we have An, and this is the matrix A, all the things on the left, but in the purple color. And what's the B vector? B vector is just the right-hand side we already know that is some numbers we know B1, B2, and then all the ways to Bn. And the X vector is the unknowns, and then we want to solve. That is the things we want to solve, and it's just a vector, and then it's just x1, x2, and to the xn. And this is the matrix format. And now we are going to put some assumptions on this system of equation, because from the linear algebra class, you already know that for linear system of equation, you have 3 cases. Case 1, no solution. Case 2, unique solution. Case 3, many solution. And it could be infinite solution here. So I just say many solution. So here we are focusing on the case 2, unique solution. And from the linear algebras knowledge, and then what does it mean for the case 2 for the matrix A? And from the linear algebra knowledge, and then we already know that, which means that the determinant of the A does not equal to 0. And which means that the A is a non-singular matrix. So we put such an assumptions on the matrix A, and for the following discussions, because we are focusing on the case 2, where we have unique solution. And if the determinant of the A has a unique solution, the determinant does not equal 0, and then it also means that A has an inverse. And in the matrix format, and actually Ax equals to B has a solution, and the X equals to the A inverse B, right? And this is from some linear algebra things. Actually, you can just get the inverse of the A and then do the multiplication here, but it takes a lot of time if you try to find the inverse. I know you have the difficult time in trying to find the inverse during the row exchange, row operation, and then that I know you hate to do that. But so now let's do some things that would make our mind easier. And so that's the things. But before we move to the method part, and then once again, we need to get some linear algebra things. So let's get some linear algebra knowledge here to help us to get some simple methods to solve the linear system equation. First of all, I know you already know the matrix, the definition of matrix. And then now I'm going to give you some knowledge you need to know. Which knowledge you need to know? Let me see. I don't think you need to know a lot of things. So let me just get the things easier for you to know. Okay, so in case that I am going to skip a lot of things here. Okay, I think you don't need to know a lot of pre-knowledge about the linear algebra, because I still assume that you already know the matrix and then vector, and then the matrix and vectors multiplication. Is it okay to skip the matrix introduction here? What is the determinant? What is the vector? What is the matrix? Because from the previous quarter, some students just complain they are learning repeated knowledge. That is the same thing from the linear algebra class. So I'm going to skip the review on the linear algebra things. So let's go to just solve the linear equation. So let's see. We have some easy to solve system here. It is easy to solve system. And so the very first case 1, this is the easy to solve system, and the very basic one is the diagonal matrix, and we just have some non-zero things on the diagonal. And don't forget that we are assuming that this is a non-singular matrix, which means that here the determinant of the A is just the determinant of A is just the multiplications of the product of the diagonal element, right? And then it does not equal to 0, which means that the AII does not equal to 0 here, right? And here, this is the implication. And so for here, this system of equation AX equals to B is easy to solve. And what's the solution? The solution is quite simple. And then if you translate it into the original version of the system equation, and then the first equation is just A11 times X1 equals to B1, and then second equation is just A22 X2 equals to B2, and so on and so forth, which means that the solution, it should be, the solutions is Xi equals to the Bi divided by AII for all the I equals to 1 to the n. And this is the easy case. And there's another more complicated case, and then that is the case 2. And it's a little bit complicated compared to this system. And then we have the A, and you will see this again and again. We love this because it's lower triangular matrix. And you will see this in the Math 104B, and then if you go to the Math 104C, and then you will see it again, because people love this one. Lower triangular matrix. And also we assume that this one is non-singular as well. Throughout this section, and then we just focus on the non-singular matrix. And lower triangular, and then which means that we only have non-zero things at the lower triangular part. And I'm going to skip the writing here. The things in between, AN1, and then this is AN2, and then all the way to the ANN. And then this is the lower triangular part, and then we have non-zero things on this part. And all the things above, they are 0. And this one is easy because, so let's see, the original equations, original version of the equation, AX equals to B, and then it could be written in this way. The very first equation is just A11X1 equals to B1. And then the second equation is just the A21X1 and the A22X2 equals to B2. And then I'm going to skip writing the things below here. And our idea to solve this equation is from the top to the bottom. So from the top, that is the first equations we have here. And then we immediately get this, the solution for the X1 solution. This is the solution part. And then X1 is just equals to the B1 equals to divided by the A11. And so if we want to go forward, and then we already know the value X1, right? And then A21 is just the A21 is just the coefficient, A22 is just a coefficient, B2 is some number we already know in the on the right hand side. So the only things we need to solve for the second equations here is X2. So here we can have X2. So from the step 1, we already get the X1 value, and then we copy here. So we already get the value for this one, value for this one, value for this one, and this one. and we only need to solve for the x2. So the x2, we get this. The b x2 equals to b2, and then minus a21, x1, and then divided by a22. And so on and so forth. And then you have the xn, which means that at this step, xn, you already know the x1 value, x2 value, and the xn minus 1 value. So for the xn, you just need to solve for the xn and then by bn minus the left-hand side, all the things except for the besides the xn term. So I have an1 x1 plus an2 x2 because before this step, and then we already know all the values for the x1 to the xn minus 1, and then divided by the coefficient a and n, and this is the solution. And we say this is the forward substitutions process. This is the forward substitutions process. And which means that we are proceeding from the top to the end. And this is the case 2. And there's another case we love. And then this is quite symmetric to the case 2. And then the case 3 here. The case 3 here. We have another matrix, but it's quite symmetric to the matrix we have just now. But now we have, let me just write down the name of this matrix. This is the upper right triangular matrix. And this time I have the non-zero things at A11, A12, A13. Let me skip writing these things, and all the way to A1n and ANN here, ANN, and then all the things here, and then A22 here, and then all the things in between, and then they are the non-zero part. And below here, and then below the diagonal here, all the things are 0. So if I write the AX equals to B into the original format, and then what can I get? I get, so from the bottom, I have ANN, XN equals to BN. And then the last 2 equations, so this is the last one. And then the second equation here, we got AN, it should be the in column n minus 1, and the in column xn, and then plus the an minus 1, and then this is the n minus 1 column, n minus 1 row, and then xn minus 1, and then plus the bn minus 1. So the idea for this equation, linear system equation, is solving the linear system equation from the bottom to the top. And for the solutions, I got, so the solution here, I got xn, and then equals to the bn over ann, and then xn minus 1 is just a bn minus 1, and then minus the left-hand side with the values we already know, bmn and ANN minus 1, AN minus 1, and the XN, and then divided by the AN minus 1, N minus 1, and then all the way to X1. The X1 is just the B1 value minus the left-hand side, the things we already know on the left-hand side, and then that is A11, A11 we don't know. For the X1 value, we don't know. So starting from A2. A1 to X2, and then plus all the way to the A1 and XN, and then divided by A11. And this is the formula. And we call this as the backward substitution process. Backward substitution process. I'm going to stop here. And the next class, I'm going to calculate how many operations we get to finish the calculation here in the computer. So for examples, for the first step, we need to do one division, and then that is one operation, right? And then for the second step, we need to do one subtraction here, one multiplication here. So that is two operations. And then there's another division here, and then that is three operations. So we want to calculate how many operations we need to get the all the solution here. And then later on, you can compare the computational cost among all the methods, and then to see which one is more efficient. And that's all the things. And see you on Monday and Wednesday. And the Wednesday is the in-class meeting.